Hello and welcome to the NPTEL MOOCs course on Foundation for Virtual and Augmented Reality System. We are going to continue our discussion on VR navigation experience optimization, which we started earlier. So, earlier we talked about one way to address the problem of minimization of the possibility of CS or cyber sickness in a system controlled virtual tour. And how we did that? We made use of one approach where we tried to figure out an optimal path covering all vertices in a given graph representing the virtual world, which can be traversed in minimum time. That was one approach. There is one more approach which we are going to talk about in this lecture. Now, that other approach is essentially to find out an optimal path covering maximum number of points of interests or POIs given some time constraint. So, earlier we did not have a time constraint. Our objective was to find a path covering all vertices that can be traversed in minimum time. Now, we are imposing one time constraint and our objective is to find out a path given this time constraint where the number of POIs covered will be maximum. So, in order to find that time constraint, time threshold, we need to define such a threshold, time threshold. So, earlier we saw that how to compute an optimal tour where the path covers all nodes in minimum time. The problem is that that minimum time may still be more than the time typically associated with onset of cyber sickness. So, that minimum time, although it is minimum given all possible paths, may still be responsible for inducing cyber sickness. It may still be more than the time threshold above which CS occurred. So, we are talking of something called a time threshold. So, essentially our objective should be to restrict the movement time or the experience time of the user or the VR exposure time of the user within this threshold. If we cross it, then there is a possibility of cyber sickness. Now, let us call this time threshold TH as shown here. So, essentially what we are trying to do, we can find an optimal path that completes within the threshold time. Now, when I say complete, essentially that means that the user should be able to cover the optimal path within this time threshold. And this time threshold can be the duration of the virtual tour, maximum duration of the virtual tour. Now, of course, there is no easy way to find out the time threshold. Of course, there are some studies which recommended some thresholds which depends on the content. Sometimes it may also depend on the speed of movement and so on. And we can obtain the threshold value through some study, empirical study with limited number of users. That is one possibility. We can also use some pre-existing study results to decide on a threshold. Now, when we are talking of a time threshold and when we are talking of covering a tour or completing a tour within the given time threshold, it is not mandatory and not always possible also to visit every single node or vertices, every single node or vertex which represents the points of interests. So, essentially here what we are saying is that we want the user to complete a tour within a given time threshold, and during that tour we are fully aware of the fact that the user may not be able to cover all points of interest, unlike in the previous approach. Now, in order to take this into account to formulate our overall problem, we defined a term called the importance of every node. How important a node is. Unless we know the importance, we do not know which nodes to cover within the given time threshold. In order to do that, we can define an importance function, a function that computes importance or assigns importance to every node, which is in the form f v maps to the set of positive real numbers. In other words, every vertex is mapped to every vertex or every point of interest v belonging to the set of v maps to a positive real number, which indicates the importance. So, we are capturing the importance in terms of a positive real number. The more the number is, the higher the importance. Then once we define the idea of importance of every node, then what we can do? We can compute total importance of a given path. Suppose we have a path P containing the nodes V1 to Vn. Now, each node has its importance. So, then total importance of the path can be defined as Fp, which is a summation of Fvi, where I varies from 1 to n, n is the number of nodes in the path. It is a quite obvious formulation that to identify or determine total importance, we simply add up the individual importance of each node in a given path. So, then in terms of that, we can have a problem statement, that is, we want to maximize Fp, that is the total importance, for paths that can be completed within time threshold Th. In other words, we want to basically identify a path which takes time less than or equal to the threshold time, but in which we are maximizing the total importance. Now, there is another important aspect that needs to be considered, which is the waiting time. So, at a given point of interest, the user is expected to spend some time to inspect, to do something with that point of interest, as we have indicated in our earlier lectures during the experiments what we have done. So, this waiting time is also a concern when we are trying to figure out a path maximizing the total importance. Now, this waiting time is essentially the time required by user to inspect or interact with a particular object at a node, that is the point of interest. So, like the importance function, we can also have a waiting time function. So, we can define this function, waiting time function, as W, where V is mapped to a real positive number. In other words, every node is mapped to a real positive number, which indicates the maximum time required to inspect or interact with the object that is there at V. So, this is the maximum time a user requires to spend at the point of interest. So, now we have two quantities, one is importance, other one is waiting time. So, two quantities associated with each node, one is importance, other one is the waiting time. Like total importance, we can also calculate total waiting time in a similar manner. Suppose we have a path P having all these vertices V1 to Vn, n nodes. Each node has an associated waiting time. Then total waiting time W capital P equal to summation of individual waiting times for all the nodes I equal to 1 to n. It is again quite obvious, like the total importance calculated earlier. Then we need to revise our earlier problem statement. What is that revision? We want to maximize the total importance for paths that complete within the time threshold Th, taking into account the waiting time. So, essentially what we want to state is Tp plus Wp must be less than equal to T threshold, where we are also maximizing Fp. Now, how to solve this? This is a well known problem in operation research. It is called a generalization of a well known problem, that is vehicle routing problem, or VRP. This is called VRP with profit, or VRPP. For more details on this problem, you can refer to the material cited at the end of this lecture. So, the idea here is that we do not need to visit all the nodes. Instead, we want to maximize profit within the given time constraint. So, here the profit is in terms of importance of the nodes. So, we want to maximize the importance within the given time constraint without necessarily requiring us to visit all the nodes. Like in the previous approach where we talked about TRP solvers, so existing tools available to solve the travelling salesman problem, here also we can make use of existing VRPP solvers. So, vehicle routing problem with profit solver to get the optimum path that maximizes profit within the given time constraint, that is the threshold time, and maximizes profit is essentially maximizes importance, total importance. So, in other words, we want to get a path that lets the user visit maximum number of most important POIs. So, this is the rephrasing of the overall problem that we are trying to solve. And if you can look at this statement, you can see that this will serve our purpose, that given a threshold, time threshold beyond which cyber sickness may occur, we want to restrict the user's exposure below the threshold time, and within that time we want to ensure that the user is able to visit most important POIs, as many as possible. So, essentially we are trying to figure out such a path that will achieve these objectives. So, let us quickly go through the algorithm. So, input is the graph. Remember that during our earlier discussion we talked about converting the virtual environment to a graph, which not necessarily is a complete graph, but fully connected graph. So, we have this original graph G having the vertex set V and edge set E epsilon, along with the importance F and waiting time W specified for each of the nodes. And the output that we want is this optimal path P, where F is maximized and the total travelling time is less than the threshold, travelling time plus wait time. So, earlier we talked about only travelling time, but now we also have to take into account the wait time. So, travelling time plus wait time, which together represents the total exposure time, must be less than the time threshold. So, first thing is like before, what we need to do is compute the complete graph G dash, where we will be replacing the edges that are not directly connected with the shortest path between those vertices. This is what we did before also. So, same thing we will be doing here, convert the graph to a complete graph. Then again second stage is also same, replace the edge weights, which is originally the Euclidean distance between the two nodes, in the modified graph with the travel time t as we did before, where travel time we compute using the natural walking model. Then once this is given, also we have separately specified the importance and the wait time. So, we then need to use the VRPP solver with input the final graph, that is G double dash, which contains vertices and edges, where the edges are weighted with the duration of travel between the vertices, which defines the edges. So, essentially we will be using a solver on this modified graph G double dash, and also we will be providing the input values for f, the waiting the importance of each node, and w, that is the waiting time for each node, to get the optimal path p opt. So, here we will be using the solvers, solve VRPP, where the input is G double dash, f and w. Then we get the output as p opt. Now, like before, what we need to do is basically modify the output to reflect the original graph. So, what we need to do is, there will be edges that were not originally connected in the virtual graph virtual world representation, but we introduced hypothetical edges in the form of shortest paths. So, we need to replace those edges with to reflect the original nature of the graph. So, replace hypothetical edges joining V I V j with the shortest path V I V j. Then we need to return the optimal path, which is modified after replacing the edges with the shortest path. So, this is the algorithm, that is, we are first creating the graph, then converting it to a complete graph, then converting it to a graph with edge weights equal to the travel duration, where travel is the duration is computed using the natural walking model to give realistic experience. Then this graph along with the importance and wait time at each node is provided as input to the VRPP solver, and then the output is further modified to replace the hypothetical edges with the shortest path, to finally get the optimum path that can be covered with maximum number of most important POIs within the given time threshold, taking into account waiting time at each node. So, let us summarize what we have learned so far. So, we are talking about experience optimization. So, there we talked about couple of approaches to take care of the CS issues, cyber sickness issues. First, we talked about identifying an optimal path in a given graph representation of a virtual environment, which can be covered in minimum time. Now, for a given large environment, this minimum time may need not be addressing the cyber sickness concern, because this time may still be large enough to induce cyber sickness. So, in order to address that, we are going for another optimal path formulation, where we talked about node weights as where we talked about the node importance and waiting times. Then we talked about one time threshold, and then we are trying to find out an optimal path that can be covered by the user within the time threshold, taking into account importance of each node and waiting time at each node. In other words, this optimal path will allow the user to cover maximum number of most important POIs within a given time threshold, taking into account the time required to spend at each point of interest to inspect or interact with the object present there. So, in the next part of the lecture, we will be having a quick look at how this idea has been put into practice in the context of our case study. So, looking forward to meet you again in the next part of this lecture, which will be the final part of this particular topic of experience optimization. So, hope you could follow the discussion. Thank you, goodbye and happy learning.